To round out our discussion about sampling, I'd like to talk a little bit now about sampling thought of more broadly, that is beyond just the sampling theorem and the Nyquist rate. The kind of thing that we think of when we think of the sampling theorem is that we're trying to sample fast enough to capture all of the action in the signal, and the signal is generating action, if you like, at a certain rate that's given by the bandwidth, and so we need to sample, proportional to the bandwidth. But really, if you think about it, what we're saying is how many degrees of freedom the signal has, that is how much variability it has, and that variability is parameterized by a certain number of numbers that we need to capture over time. And so maybe this sort of idea of sampling extends more broadly. So the sampling theorem says that if we sample a signal x of t of total bandwidth b at a rate greater than b samples per second, then we can recover x of t exactly using sinc interpolation. So this is the total bandwidth b, including plus and minus frequencies. So what is it saying? It's saying we need b numbers, or samples per second, to completely describe the signal x of t. So we can think about it in terms of data storage. How many numbers per second do we need to be measuring in order to capture x of t? And this is important because we actually sample data and restore it in a computer, so we're actually always dealing with sampled signals, unless we're doing analog electronics. So let's think about the samples that we have as data, right? And that's really the viewpoint that I want to take when we think about sampling. So again, we need b numbers to represent each second of x of t. So x of t is like generating new information at b numbers per second. And so that's really, we should think about it this way. It's like the rate at which new information is being generated and has to be stored. So if we use 16-bit floating point representation for each number, then we're using 16b times bits per second. So 16 times b bits per second. And so that is like, now you can think about, okay, well, what is the data rate I need to be able to maintain on the wire or wireless link that links my sensor to, my computing unit? And note that this representation is approximate because we're only storing 16b bits, so we're only storing 16 bits per number. And in reality, x of t is an analog signal, and so it has infinite precision. So one way of capturing this is something called the rate of innovation of a signal. This was defined by Vetterli and colleagues in 2002. And basically the idea is the rate of innovation of a signal is a measure of how many numbers it takes to describe the signal per unit time. So we can see what that means when we look through a formula where we basically say, okay, x of t is some coefficient Cn times some function phi that's shifted by nt, so that's basically every t seconds we're going to be getting a new number, Cn. So we get one real number, Cn, every t seconds. And so we define the rate of innovation to be just rho is 1 over t. So that's kind of how fast are the new numbers being generated or new numbers being needed. So we can make this model a bit more complicated if we, instead of saying it's sampled, so this is regular sampling. And if we instead shift to talking about just arbitrary times, then we can say like, okay, well maybe I have 15 samples in this second, but I only had 2 samples in this other second and 1 in the next second. So that's a total of 18. So maybe I'm only getting like over 3 seconds. So really the rate is kind of like on average 6 numbers per second, right? So we can also allow these phi functions to change. We can think of this phi as like being like the sinc function, right? We're thinking about sinc functions. We're interpolating using sinc functions. So these phi could be a sinc function, and this could be for the regular sampling theorem. So phi is a sinc function, and so we can think about it that way as a generalization of our regular sampling theorem. So one example of this is, a lot of signals are not necessarily band limited, but they might be, for example, a sum of delta functions. You might have discrete events like photons arriving at a photodetector. Those are just like spikes that happen at each time unit at various random times, for example. And so we have these arbitrary times. So we can see we have over here we have our time domain signal. If you look at the frequency representation that is Fourier transform of this string of delta functions, you get this like super wiggly thing. It's not particularly band limited, so we're not going to get something that nice. But if we had a sink in time, right? This is a sink, then we get a box in frequency. So that's nice and band limited. This one is not band limited. Or we could have this polynomial, right, where we sample this say polynomial or sum of sines or cosines, right? I guess cosines. And if we're sampling a sum of cosines in particular, you will see that it's band limited because the frequencies are only at the sinusoidal components. That is, we get these delta functions from cosines at different frequencies, and so that whole thing is band limited. So this is band limited, and this middle one is band limited, but this is not band limited. But if you think about it, I can represent this signal by 1, 2, 3, 4, 5, 6, 7, 8. I only need to represent it with eight numbers for the magnitude and 8 numbers for the location. So it only takes 16 numbers to describe this signal, but it takes a lot of numbers to represent the sinc signal or the sum of cosines. So this signal here is very simple. So in some sense, we should be able to sample something and sample something and be able to recover this very simple signal. And the idea is that if this signal has you can write it down in a simple way with a simple formula, then hopefully you can like sample it and store it in a simple way. So as a more complicated example, you could have piecewise linear functions. And if you have this piecewise linear function, you can see its frequency is also not band limited. But here we have this band limited signal, this sinc function in the middle, and then we also have we can have a pretty much band limited signal here, which is like smooth and is still band limited. But this piecewise linear function, again, I just need to describe the slope here, the inflection point here, the slope here, the inflection point here, the slope here, inflection, and slope. So this signal is defined by 1, 2, 3, 4, 5, 6, 7 numbers. And so representing it in terms of the frequency domain seems very wasteful. So if we look at these impulse functions as a template, the question is how to sample this? Right, that's the question we want to ask ourselves. And then how can we get it so that we're only measuring this small number of numbers per second? And that's exactly what we're storing in the computer, as opposed to trying to sample this super high frequency signal and using the Nyquist rate, we would have to sample it at a huge number of samples per second, like potentially infinite. So the key is that we don't get to observe our x of t directly, but only through some sort of measurement system. So here we can think of this as the sensor. This is the phenomenon. So if you think about it, the sensor, this could be a low-pass filter, for example. It could be that our sensor acts like a low-pass filter, in which case sampling using, this is regular sampling. And this is a continuous to discrete time. And we're going to get essentially at the output, we're going to get, remember this is this inner product, but it's an inner product of slash convolution, because this thing is a convolution. So we're actually going to, our overall sensor system, we can model it like this, in which case we're only getting these samples here, and the question is, from these samples here, can we reconstruct the original signal x? So it turns out that in many cases we can recover x from just these, from this discrete time signal, this dt signal, which is a sampled version of y. the output of our measurement system. Again, remember this is the sensor. So that's actually pretty cool, and this is what the whole finite rate of innovation is really about, is being able to say, well, this signal has a simple structure. If I process it in the right way, I can recover it. I can use only the right number of samples to represent it, and that I won't have to store more numbers because that signal is potentially has a very high bandwidth, even though it has a simple time domain representation. So we've seen this kind of phenomenon a lot. Transforms let us represent signals in multiple ways, and so we should be thinking more broadly about how we take a signal and represent it mathematically beyond just sampling. So we've seen, of course, we have the time domain signal, we have the Laplace domain or Z domain signal, we have the frequency domain, and sometimes we might have these CT Fourier series. And so you can take a signal that looks like this, and if you actually take its Fourier transform, you might see, oh, it actually is band limited between minus b and b here. So in transforms, we have like an analysis formula. An analysis formula says, how do I take a time domain signal here and represent it as a frequency domain signal here? Again, time domain, frequency domain. And then we have a synthesis formula that is, how do I take my frequency description of the frequency content of a signal and actually synthesize my original time domain signal? Right? And what are these synthesis formulas for the Fourier transform story, the story that we've been telling in the class, says that lots of signals of interest can be represented as sums of complex exponentials, or linear combinations of complex exponentials, or a mixture of complex exponentials. So we're saying, like, many natural signals, because they're band limited, we can write them as like this kind of mixture of lower frequency sinusoids, and this gives us an alternative way of representing the signal. And we can think of these transforms then, because it's equivalent to think about that this frequency domain signal is again equivalent to this time domain signal, right? Because you can go backwards in the transform. You can go take the inverse transform or take the forward transform. So one way you can think about this as like a change of basis when you think about the vector space of signals. Remember, we talked way back at the beginning of the class about how signals can be thought of as vectors in a vector space. So we can think of these transforms as like a change of basis. And for those who've taken linear algebra, this might make a little bit more sense. But the idea is we're just writing it in a different way. We're writing it in terms of different functions. So instead of writing it in terms of in the time domain, we're writing it in the frequency domain. So we're writing it as a combination of complex exponentials as opposed to the time domain samples. So these synthesis formulas, of course, are integrals, so they're kind of complicated to compute numerically. But our synthesis formula could be very simple if our x of t is very simple. So if x of t is periodic, then we know that it's a sum of sinusoids. And in fact, we can say it's a sum of maybe sinusoids at different frequencies k omega naught, for k equals, -1, -2, -3, dot, 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 and 1, 2, 3, dot, 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 right? So we have these two summations. So we're saying it's got a sort of simple representation, and we're just saying that x of t is a linear combination of complex exponentials, and they're actually like harmonically related because they're all integer multiples of the same frequency omega naught. And this is exactly what the CT Fourier series is. Continuous time Fourier series is just a way of writing our signal as in a simpler way as just a sum of these complex exponentials with coefficients, with some coefficients. And so this is not so the point is that this is not an integral, right? This is not an integral. Right? And so many signals we can think of them then as, if I can write it as a sum of terms, kind of like we had those phi functions before. If I can write it as a sum of terms, then I've got a simple representation for the signal. And maybe I can then just store the AKs, for example, in this example here. So still we have a problem where the CTFS formula is an infinite sum. So it's also complicated to compute numerically. I mean, we replace the integral with a sum, but now it's a sum over an infinite number of elements. So if this Fourier series has a finite number of terms, so it only goes from minus k to k, then we only need two k plus 1 numbers. That's the ak from k equals little k equals minus k plus 1 dot 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 up to k. So we need two k plus 1 numbers to represent x of t. So we actually don't need, for example, we don't need to store an analog signal. We don't need to sample it regularly and have kind of like a regular sampling, so we're getting two b samples per second. We can actually just write down two k plus 1 numbers, and that's it. And so that's all we need to do to describe the signal. And this is like why synthesizers work, right? Because synthesizers aren't summing up an infinite number of sinusoids. They're saying, okay, I want to synthesize a violin. I'm going to add up frequency components, up to a certain level, up to some capital K, and that's going to be how I represent my violin signal, and hopefully it'll sound enough like a violin. But of course, not all signals are complex exponentials. We can't just say like, every signal will have a simple representation as a finite combination of complex exponentials, like with the Fourier series. But we could look at like piecewise constant functions. So remember, we saw all these examples of signals that look like this, square waves, or like just signals which kind of were step functions, basically adding steps and going up and down. But we can imagine we have only a finite number of terms, say from k equals 1 to capital K. We basically say here's like t, here's t1, here's t2, here's t3, and so on. So, and here's say tk. So we can describe this piecewise constant function in terms of just two k numbers, the heights at which I jump using the step function and the place where I jump using the step function. So again, we only need two k numbers to store this signal. And if you think about this signal has infinite bandwidth. So Nyquist says we can't store it using a finite number of samples per second. And that's samples per second. So that's actually still going to be an infinite number of samples. So Nyquist says we can't even store it with a finite number of samples per second. And here I'm telling you, actually you just need to store 2k numbers. So this signal is really easy to store in a computer, but Nyquist will tell you that you have to, sample it at a very high rate if you want to get even close to sampling to get representing it, and you're going to get aliasing and all sorts of other bad stuff. This is, but if we write it down in the right way. So the point is, if we write it down in the right way, we can see that we only need to store 2k numbers. So this is like the essence of like data compression in a sense. So this whole discussion that I've been having so far is basically the idea of signal representation. So we want to be able to write down our signals in terms of simpler signals. So we had sync functions. Sync functions is the way that we know out of Nyquist to write down a signal in terms of simpler functions. But you have these other representations for some signals where it's just a finite number of impulse functions that has infinite bandwidth, but it's only got a finite number of positions where the impulse functions are and the heights. The piecewise constant function we just talked about, those also can be described with a finite number of numbers. So we can look at so the idea is like we would need 3k numbers to write a signal that has some can be written as a finite combination of some base signals phi shifted by tk and then multiplied by ak. So if one way to make this concrete is if we think about x of t equals 3t squared minus 2t plus 1. Here we need only 3 numbers, so we need 3 numbers here. But if I said x of t is equal to 2 cosine t minus 5 plus 3t squared minus 4 t minus 2 cubed, right? I would need to store a bunch of numbers. I need to store this 5, this 2, this 3, maybe this 2, this 3, this 2, this 4, and maybe a number that indicates that I have a cosine here. And so here you'd see immediately there's a shift of 0 here, so I have to store another number here. So you see we're going to get 9 numbers to store this. So that's the AKs, the NKs, and the TKs. So it looks a little confusing, and this is a little confusing in written abstractly like this. But the idea is if I can write a simple formula for x, I just need to sum up all the numbers that I need in that simple formula to represent x. And that's what I should store instead of storing like sampling the signal like a la Nyquist. But this is a what we call this a representation. This is a signal representation because we're saying, this is how I can write down a formula for my signal. I represent the signal mathematically. So modern machine learning uses many techniques to learn representations of signals, and one approach is something called a deep autoencoder, and this deep autoencoder can learn nonlinear representations of the data. So this takes us out of the realm of linear systems into sort of a nonlinear system setting. But inside these autoencoders, you sometimes have convolutions and so on. So there's sort of a combination of linear and nonlinear. So how does an autoencoder work? It's got 2 blocks, an encoder and a decoder. And an encoder passes a signal through some linear filters followed by some nonlinear activations, and it does this repeatedly. So there's a linear part and a nonlinear part and a linear part and a nonlinear part. And then we get, and in the end, you get something that's smaller than the original. So if this was like n numbers here, you'd say like this thing is like k numbers here, right? So you get a compression ratio of k over n. So that's the compression factor, or if you like n over k. But k over n is like what fraction of how much smaller is my code. This code is the representation, internal representation of the signal that you have, and then the decoder will map this code in the same kind of linear followed by nonlinear way in order to get an approximation x prime. And so the hope is that x is approximately equal to x prime, right? And you can do this for images, you can do this for representations of documents and language. And so the idea is, can I use this as a compression method to compress my input signal into something smaller? For n samples of my input layer, input signal, can I get only k out, and then reconstruct something that's approximately like what I had before. And so this is the idea of an autoencoder, and these are used all over the place, especially as part of bigger machine learning AI models. So for discrete signals, if we have discrete time signals, if they're finite length, we might have encountered the discrete Fourier transform, which said that like our Fourier coefficients are just a matrix times the input signal. So this DFT is like the same as the FFT that we were using in the labs. And so remember, you have to choose a length for your DFT, and usually we choose something that's a power of 2 because that means we can use the fast Fourier transform. So you're basically, your whole transform now really is change of basis, it's just saying I multiply my original time domain signal x with a matrix which changes it into a new representation, capital X, which is the Fourier transform, the discrete Fourier transform of the signal little x. So where is this? Where in what way could this be useful in our terms of our representation learning? Well, we can consider signals which have only s much smaller than n. So this means much smaller than. And non-zero DFT coefficient. So that is, we can say it's a linear combination of just a small number of complex exponentials. And so, and what we're thinking is like maybe n is a million and s is 10. So we're thinking about like instead of storing a million numbers, right, which are the Fourier coefficients, which are the time domain signal, of the signal, we really should only store 10 numbers or 20 numbers, where the frequencies and the magnitudes in the Fourier transform. So what does this mean? What we say that if this is true, that x has a sparse representation in terms of the DFT. So that is, we can write it in terms of s numbers or s coefficients, and we have our DFT coefficient, and then we have our complex exponential. So this is, again, the idea that I can write x as a finite combination of complex exponentials or finite combination of template functions. And so, again, what do we need to store here? We need kr and s. We need kr and xkr. What is kr? Well, kr is, so these are integers from 0 to n minus 1. And we can think of these as real numbers. So the question is, how much do we have to store in order to represent the signal? Well, the DFT matrix, okay, we said it was a change of basis. So if we think about it that way, then we could say, well, like, our signal x is actually just, say a combination. Here's s is equal to 4. It's a combination of linear combination of 4 vectors, that is 4 columns of the DFT matrix. So we need to store s real numbers, that is these a's. These are the DFT coefficients. And we need to store s indices, that is these subscripts here. Right? So if we have 16-bit floats for the numbers, and then we have an integer for the indices, we're going to have s times 16 for the floating point numbers and s times log n, because we only because they can only go up to capital. The index can go from up to capital N. And so this is what we have to store. And if you think about this number, this is so much tinier than if I had 1024 coefficients and 16-bit floats. So if I wanted to store the original signal x, it's going to take, 16 kilobits to store that signal. But it's going to store, so I guess 2 megabytes. Whereas here I can store 16 times 4 plus 4 times 10. So 16 times 4 plus 4 times 10, so that's 40. 64 plus 40 is 104. So we have 104. We have 104 bits, and here we have 16 times 1024 bits. So that's a massive savings in compression, and this is like the key to making computationally efficient systems. Is if you can find good representations of your data, then you can store it much more efficiently. So this idea of sparse representation is really important in signal processing and in machine learning and a lot of numerical computation. So in terms of numerical methods, multiplying sparse vectors and matrices can be done very efficiently computationally, rather than storing a gigantic matrix which is like mostly zeros. And storing those sparse vectors and matrices can be done efficiently. So both computation and storage are efficient when you have sparsity. And empirically, we can find good sparse approximations to many signals. So that is, the idea is, can we find a way to represent our signals in a way that makes things sparse? And one way to do that is something called dictionary learning. And so in dictionary learning, what you have is you're trying to take a corpus of data. So you have y1 through yn, which are like images, for example. And what we'd like to do is create a dictionary of signals, d1 through dm, such that each y can be approximated by a sparse linear combination of at most s vectors. So basically, so this yi is going to be a sparse linear combination of these d's. So there's only s of them. We're going to only need s of them for each to represent each y. And so the metaphor here is that each of your images you can think of as a sentence, and these sentences are short. That's what s means. If s is small, the sentences are short, and it can be written using a small number of words, dj. And so you're trying to figure out what is the best set of words that can represent all the images that I have, the sentences that I have. So how does this work in image processing exactly? So what we do is we try to learn from natural images. So here's a picture of a house, and you divide this thing into little patches. So you take little patches of this house, and then you try to learn a dictionary that can describe each like square patch of the image. And then if you get instead a noisy version of this image, what you can do is you can try to clean it up by trying to make find the best fitting sparse approximation to the patches in this image. So I'll take this patch here and I'll say, oh, this is not easily described. What I want to do is like find the best S sparse approximation using the dictionary. Right, and this is a way of doing what's called denoising the image, so that I can take a messed up image and I can kind of try to remove the noise from it by having a good dictionary that represents clean images very well. So, for example, you could start with an original image. You can create a noisy image, and then one of the projects I've worked on in the last few years, we look at two different types of different dictionary learning, and you can sort of see that this one is a little better. But this is what dictionary learning will let you do in any case. Both of these are examples of dictionary learning, and you can see you can remove a lot of the speckled noise by using using this dictionary learning idea to clean up the signal. And so the house looks, it doesn't look quite as good as the original, but it's certainly a lot better than this thing here. So the idea behind sparsity and sparse representations is to come up with what they call a parsimonious, that's just a fancy way of saying cheap, or simple model for signals. So this has applications all sorts of places. A lot of applications in biomedical imaging and image reconstruction, as we saw, just this denoising thing. There's something called coded aperture photography, where you are trying to design like new types of camera systems that don't just use a CCD to charge coupled device to like capture the image, but instead alter the aperture of the camera in order to essentially sample the visual field in a special way. And you can get away with maybe cheaper hardware for doing this. So you can still get really good cameras, but like with much cheaper design. You don't need to have a gigantic CCD. There's also applications in recommender systems, which are a machine learning method. So, for example, when Amazon or another online shopping portal has suggestions for what products you might be interested in. And that's what's called a recommender system, and this has to do in order to build recommender systems, you're essentially doing what we call low rank modeling, which is is related to these sort of parsimonious representations. You're saying that sort of the ways in which products and people's interest in the products has kind of a simple sparse or simple structure that we can exploit to try and learn that relation from data. And finally, deep learning is really revolutionizing machine learning and AI, and there's a lot of work in trying to sparsify deep learning models in order to make them more computationally efficient. So the basic idea I think we want to take away from this is that when you acquire or measure a signal, it may be very complex and high dimensional the way in which you measure it. Like an MRI is very complicated. It's got a lot of numbers in it. But if you look at it the right way, that is, you find a simple model or a sparse representation, a simple representation, you can make it much easier to handle computationally. You can store things more efficiently. You can compute things more efficiently. And so really it's like you need to find the right way of looking at your data. And this is sort of where the ideas from this class kind of connect and dovetail in with ideas you see in data science and machine learning and other related fields. So just as a recap, the sampling theorem is a statement about the degrees of freedom, or we can think about it as the rate of innovation of a band-limited signal. But this rate of innovation idea, that is the number of samples that you're generating per second, extends to non-band-limited signals as well. And we can think of these, if we have like a simple, sparse, or finite representation of a signal with just like 2k plus numbers or 3k numbers, we can think of these as the degrees of freedom that the signal has. That is, how many numbers do I need to describe the signal? And that's very much related to how efficiently to synthesize the signal and to represent the signal, and therefore store the signal. So if you have the right representation, you can store the signal very efficiently, and you can do significantly better than something that Nyquist would suggest, because you might have an infinite bandwidth signal, but it still has a simple representation. And finding these sparse representations can have a lot of benefits for storage and computation. So, as you go forward, thinking of, when you encounter some of these related ideas in future classes, or when you're on, in a job and you're trying to use some of these techniques like a autoencoder or something like that, I think this hopefully will provide some context for you in terms of understanding why these issues are important. Why do we care about sparsity, and why do we care about efficient representations? And that's a follow-on to what we've been talking about in this class so far.